Okay, I wanted to discuss a technique of solving systems of linear equations that's very common here. It is called Gaussian elimination. Okay, it's used in computer programs and calculators all over the place. Okay, this is very numerically stable. You don't have to worry about that, what that means. System used for solving systems of linear equations. Okay, the first thing we need to talk about is something called the augmented matrix. Ooh, sounds fancy. The augmented matrix of a system. Suppose I have a system like the following example. 2x minus 7y equals 3 and x plus 5y equals 4. Let's create the corresponding augmented matrix of the system. Okay, let's talk about, it's this just array of numbers here. Okay, it's just an array of numbers. 2, negative 7, 3, 1, 5, 4. Now to introduce just a little terminology here, starting from the upper left-hand corner, okay, the first row right there that I'm pointing at is read across. So rows go across, okay? So the first row is 2, negative 7, 3. The second row is 1, 5, 4, okay? Then we've got some other things here. We've got things called columns here, okay? The first column, again, starting at the upper left-hand corner like reading a book. See, the first column, columns go up and down like columns that hold up roofs on buildings and stuff, right? Okay, so the first column would be read 2, 1. The second column would be read negative 7, 5. And then the last column, or the third column, is 3, 4. Okay, so this particular matrix has what? 2 rows and 3 columns. We would write its dimensions this way, 2 by 3. Okay, so our convention is always what? The first number is the number of rows. Okay, it's just the way the convention goes. The second number is the number of columns. So it's 2 by 3. 2 times 3 is 6, is the total number of what we call entries in the matrix, right? That's the total number of numbers actually appearing in the array. By the way, in computer science, the word matrix is often replaced by the word array. You might have heard that before. Now, with the augmented matrix, okay, that's a particular type of matrix corresponding to a system. You see what I've done here? I've written my matrix this way with the various constants involved. 2, negative 7, 3, 1. Okay, the 1 is implicit there, by the way. 1, 5, and 4. The 2, negative 7 and the 1, 5 are what? Those are the coefficients of x and y respectively in the system, okay? Over on the left-hand side you can see, okay? So I actually labeled the first column x, okay? This means what? The first value is 2, okay, in the first equation, so that's 2x. Okay, this value is 1, so we've got 1x in the second equation. Okay, to that we're adding negative 7y, so I've got the second column labeled y. Okay, and you see in the second equation, I've got 5y, so I have 5 in the y column there in the matrix here. Okay, now I've also got this little dashed line here. Okay, this little dashed line separates the following. It separates coefficients, right? Okay, so those are just the numbers multiplying on x and y. It separates the coefficients from the constants. You guys notice here that there's no x's or y's on these, the 3 and 4. So this is the column of constants at the end. And this little dashed line, or sometimes you'll see it in some books and places, a solid line, okay? It just separates the coefficients from the constant terms over on this side, okay? Alrighty, so I've drawn all over that, but that's the augmented matrix corresponding to that system. Okay, let's do it reverse. Suppose I had this augmented matrix, 2, 5, 8, negative 1, 4, 7. Okay, with the first column labeled with x and the second column labeled with y. No column on the, no label on the third column. what system would that correspond to? That would correspond to 2x plus 5y equals 8, and what? Negative 1x, or better written just negative x, plus 4y is 7. Okay, so you should be able to go back and forth between an augmented matrix and the actual system of linear equations involved. Now, the reason why in Gaussian elimination we just write these as so-called these augmented matrix is because when we're working on trying to solve a system of linear equations using this elimination technique that we'll talk about, all that's actually happening, all that's involved is operating on these constants here. So all operations will involve these constants here, and these x's and y's would just get carried along. So we don't write them all the time, just as a shortcut to save us some writing. Also, in a computer, this is a much easier way to store the problem here. Okay, you just have in the computer register places where these numbers go. Okay, there's just places where these numbers go, and the computer knows to operate on those in a certain way. Okay, so this is very much set up for what you need to do on your computer or your calculator. Okay, and later on I will show on a TI-84 how you can actually do this on a calculator. Okay, but let's continue with this. Okay, let's take another one. What's this system? Okay, just take a look at it. 258, negative 147. Okay. Oh, wait, that's the same one. Never mind. Okay. Why did I do that twice? Oh, well. Anyways, here's another one that's really important here. Okay. I've got 104015, and then it's labeled x and y. Again, there may be other variables here. It may be, w and z or something. But it's labeled with x and y. How would we read that? What would that system correspond to? That would be 1x plus 0y. So that would be actually x plus 0y is 4, right? But 0y is 0, so that's really just saying what? X is 4. So this line, that first row, is actually just saying that x is 4. How about this second row? What is that saying? 0x and 1y is 5, as I've written over here, but that really means that what? Just y is 5. So this is a fancy way, if you want to think of it, saying x is 4, y is 5. And that's the type of thing we want in our solutions, right? We want to just, if possible, to just read off our solution, x is 4 and y equals 5 or whatever. Okay, now this particular form we have up here is one example of what we're going to call row-reduced echelon form. Row-reduced echelon form. In many calculators, such as the TIs, the Texas Instruments, you'll have this thing you'll see in your calculator, RREF. That's the perfect setup to read a solution, row-reduced echelon form, and we'll explain exactly what that means in just a little while, okay? Just a little bit. Let's take a look at this one, okay, this example here. Reading across, okay, so the first row, I've got the labels, I should mention X, Y, Z there, you can see. I've got what? 1, 0, negative 1, 5, okay? The second row, 0, 1, 0, 7. The bottom row is all zeros, okay? Let's start at the bottom row, just for a second here. What is this saying? It's saying 0x plus 0y plus 0z is 0. 0 times any number is 0, and 0 added to 0 is 0. So this line is actually saying ultimately that 0 is equal to 0. That's great. Okay, we already knew that. That's really conveying no useful information to us. But let me explain, this does appear in certain calculations as we go through them, rows like this. So I'm going to mention it, okay? You'll see that better as we go along here. Let's go to these non-trivial rows up here. Let's go to the first row, for example. By the way, this matrix is also in row-reduced echelon form. Okay, but again, I haven't explained completely what that means yet, so just hang in there. But let's read this. What would it say? 1x plus 0y plus negative 1z is 5. Okay, in short, x minus z is 5. Do you see that? X minus z equals 5. Okay, how about the second row? 0x plus 1y plus 0z is 7. That boils down to use a chemistry analogy, y is 7. Okay, y equals 7. If this was the end product of our elimination, which it probably would be, it would be. Okay, most of the time you're not given problems this easy. So you would work our elimination method down to this point where it's row-reduced echelon form, and you'd read off the answer, and the answer would look like something like this. Okay, or one way to write it anyway. There's actually infinitely many solutions here. Okay, infinitely many solutions. Do you remember what we said about a system of linear equations in the last video? Every linear system has what? Either one solution, no solutions, or infinitely many solutions. This actually has infinitely many solutions, okay, here? Because you can see here, okay, y is always 7. Y is 7, right? It's determined. But if you look at x and z, how many values of x and z can you find whose difference is 5? The answer is infinitely many, right? So if I'm talking about a solution as being what? An x, y, z triple, there's actually infinitely many solutions to the system. But we'll see more of these as we go along, okay? Now, let's talk about what's going to happen with Gaussian elimination. You're going to start out with some sort of system of linear equations, and you're going to create its corresponding augmented matrix, and then you're going to start performing elementary row operations, or I just call them row operations, on the rows of that augmented matrix, okay? And you're going to keep doing that till we get a certain type of form, you guessed it, the row-reduced echelon form, okay? Now, what are these elementary row operations that you can perform? They're the following. Here's a very simple one. Any two rows can be interchanged. Okay? All right? You can interchange any two rows. What would that be equivalent to doing in the system of linear equations? That'd be interchanging two equations, right? Well, that's not going to change your solution, right? Okay, so that's perfectly fine. That's perfectly fair. And we're going to see certain situations where there's an advantage in actually doing that. Okay, so it seems kind of trivial, but sometimes it's really not. Okay, let's look at our second elementary row operation. Any row can be multiplied or divided by a non-zero constant. Okay, now when I multiply on a row, I'm going to multiply every element of that row by that non-zero constant. That includes what? The constant term on the other side of the what? Dashed vertical line. Okay? The other side of that dashed vertical line is really standing in place of what? It's acting like an equal sign, right? It's acting like an equal sign. Okay? So think of it as multiplying on both sides of an equation by a non-zero constant. Or if you want, you can think of it as being a division multiplying by the reciprocal of a number, a non-zero number if you want. You can think of it that way too. Okay? All right? We'll be doing both here, so let's think of it that way. Okay? But you can see that's totally a fair thing to do. We've done that with equations before using the elimination method. Okay? Divided or multiplied on both sides of an equation by a non-zero constant. This time it would just be doing that operation with a whole row. Okay? Now here's the actual magic of elimination here. Gaussian elimination is a multiple of one row can be added to another row. Okay? And we're going to do that in such a way that what? Variables get eliminated in essence. Okay? And that's going to correspond to getting zeros in columns in certain places. Okay? So multiple of one row can be added to another row. Okay? So these are the three operations that we can do. Okay? 3 row operations. I'm counting number 2, multiplication or division, as a single operation there. So either one you want to do here. Okay, now you want to use these row operations until you get RREF, row reduced echelon form for your augmented matrix. And now what is that? We finally got to be careful about defining that. But you want to keep doing it until you get that form. Now here it is. Okay, rows consisting entirely of zeros lie below any non-zero rows. Okay, so if I've got a row consisting entirely of zeros, that's got to be at the bottom. Okay, all right, there might be multiple ones, but those have to be at the bottom, meaning below any rows that contain some non-zero elements. Okay, so 0 rows at the bottom, just think of it that way. Okay, now we'll be looking at different examples of these, so you shouldn't get confused here. Okay, in any non-zero row, okay, so that means some entry is non-zero, the first non-zero entry, reading from left to right, like we do in the West, reading a book, the first non-zero entry, or what we call the leading entry in that row, okay, so the first non-zero entry better be 1, okay? That's really good if it's a 1, okay? It's the best way to look at it. Okay, so the leading entry in any non-zero row better be a 1, okay? So that shouldn't be too hard to understand. Okay, this is maybe a little bit harder, but we'll see examples here. The entries in the rest of the column, oh, I'm sorry, the fourth one's difficult. This one's easy. The entries in the rest of the column of a leading entry are 0. Okay, so if I've got, a leading entry being 1, in the rest of that column, I better have zeros. Now, again, we'll be looking at these. Okay, here's the most complicated one, but it's easy to understand when you get used to it. Any leading entry is below and to the right of the leading entry in the rows above. Okay, so it's saying the leading entries, those special ones, are staggered down from left to right. Okay, so let's go ahead. Let's talk about, this is sort of an idealized situation here. This matrix, now these little stars here just represent numbers. Okay, they could be 0 even. Okay, but maybe not. Okay, this is in row reduced echelon form. Okay, what's a leading entry? That's a leading entry, and there's another leading entry. Those had better be 1s. Okay, those are the first non-zero entries in each of those 2 rows. They better be 1s. Are they? Yep. Okay, so number 2 is satisfied. By the way, there's no rows consisting entirely of zeros, so number 1 is vacuously satisfied. Okay, but number 2 is satisfied, definitely. Okay, number 3, is it satisfied? Are the entries in the rest of the column of a leading entry, are they 0? Well, here's a leading entry. I circled it, right? Is everything else in that column 0? Yep. Yeah, it looks like it. There's only one other element in that column, and that's a 0. How about this one? That's a leading entry, right? That's a leading 1, right? Is everything else in that column 0? Yes, also. Okay, there it is. So there's only 2 leading entries. This is a sort of our idealized situation. Remember how we read this off in the end? This would be saying what? 1x plus 0y is whatever that is. In essence, it would be saying x is that number. This would be saying y is that number. And that's just what we want for a solution. X equals, y equals, whatever. Okay? Alrighty. Let's talk about 3 equations here. Oh, I say unique because this shows a unique solution. Remember, linear systems, you either have a unique solution, no solution, or infinitely many solution. Let's say I had 3 equations and I worked it down and it looked like this. Can you see that this is row reduced echelon form? Okay, look at the leading entries in every row. This is a leading entry. That's the first non-zero element in the first row. This is the first non-zero element in the second row. This is the first non-zero element in the third row. Are those 1s? Yes. Are there any rows of zeros? No, so we don't have to worry about them being at the bottom or the top or any other place. Okay, so that's number 1 is vacuously satisfied. Okay, Are there zeros in the rest of the column of these leading ones, these leading entries? Do you see? Yep. Right. Okay. All right. And now are they staggered from left to right as we read down? I guess I didn't do that on this one, right? Okay. So this leading entry, okay, better be what? This is the leading entry on the second row. It better be to the right of the leading entry in the first row. Likewise, this is the leading entry in the third row. It better be to the right of the leading entry in the second row, which of course makes it what? To the right of the leading entry in the first row. Therefore, this is in what? Row reduced echelon form. All four of these are satisfied. The first one vacuously. This would once again tell us what the unique solution is. This would be saying ultimately what? X is this guy, this number. Y is this number. Z is this number. This is the most wonderful setup we could have, okay, for reading it off. This is the most perfect situation. We don't always get it, though, depending on the system of linear equations. Okay? All right, now let's actually start a problem involving Gaussian elimination. Let's look at this guy. X plus 3y is 5. 3x plus 10y is negative 4. Step 1, create the augmented matrix. Okay, so I've got 1, 3, 5, 3, 10, negative 4. I've got x in the first column, y in the second column, my little dashed line. Everything looks good. Okay? All right? All right. Now, remember, I want to get this to row reduced echelon form. Now, if you look at the leading entry here in the first row, start there. What's the leading entry in the first row? It is 1. That's perfect. That's just what I want where I want it. Hopefully I can get it to a situation so it looks just like this guy here. Okay? All right? So I've got a leading entry being 1. Okay? I didn't have to divide or multiply through in that row or perform any row interchanges or anything. I've got a 1 that I want where I want it. What don't I like about this column now? What I don't like about this column is that 3 there. Why? Well, I've got a leading entry being 1 here. What do I want in the rest of that column? I want zeros to be in the rest of that column. So somehow, using legal row operations, I want to change that into a 0. Now here's how I'm going to do it, using elementary row operations. I'm going to add a multiple of the first row to change the second row. And here's going to be my notation. I would like you to use this when you write up your work as well. It tells me what you're doing. I'm going negative 3 times the first row. Okay, so negative 3 R1, that's row 1. And I'm going to add that to row 2, see the subscript row 2, and this thing means replaces row 2. Okay, so I'm not actually changing the first row, I'm changing the second row, but I'm using the first row to change the second. Okay, so let's go ahead and do this. So I just wrote my first row again because it didn't change, but now I'm going to do this. I'm going to go negative 3 times the first row added to the second row. So I do that entry by entry. So I go negative 3 times 1 here, added to the 3 here, gives us 0. Okay? That's exactly why I'm doing this operation, just to get that 0 there. Okay? Great. But I have to do it with the entire row. Remember, you're just adding a multiple of one equation to another. That's in essence of what you're doing. Okay, like in the old elimination method. Anyway, so I'm going negative 3 times this. Okay, negative 3 times 3 is negative 9. And I want to add it to this. What would I get? I would get a 1 right there. Okay, negative 3 times this added to this would be negative 19, wouldn't it? Okay, all right, am I done? No. Okay. This is not in row reduced echelon form, but it's in pretty good form here. What's the leading entry on the second row? The leading entry is a 1. Okay, we got lucky there. The leading entry is a 1, so it's just what I want where I want it. Okay? What don't I like about this column is this guy now. I want that to be a 0. Oh, did you notice that I haven't been including the x and y? If you're doing a bunch of calculations, label your columns x and y or whatever the variables are at the beginning and at the end. There's no need to carry them through all the way through. Okay? All right, anyways, to get back to it, I've got a 1 right here, which is what I want, where I want it. I don't like this fellow. Now, how could I use that 1 to eliminate the 3? Well, I could go -3 times 1 added to the -3, and I would end up getting 0. But if I do it with this entry, I have to do it with the whole row. Because remember, this is just what? It's a shorthand for an equation. I'm adding multiples of one equation to another. Okay? All right, so this time what am I going to do? I'm going to go -3 times the second row, and I'm going to add that to the first row, and that will change or replace the first row. So you see my notation there again. Okay, now let me notice, let's go through and just pay attention what's happening with this 0 here. When I go -3 times the 0, I get 0, and I add it to the 1, I still get 1. So you see my first column is not messed up. Okay, it's still 1, 0, like I like it. Okay, all right. Now I'm not changing the second row at all, so I would actually, when I was doing this and I wrote it down, I just write the 0, 1, -19, and then the first row up here is the one being changed here. Again, emphasizing it didn't change the first column though. Okay, -3 times 1 added to 3 makes 0. That's why we did this. Hooray. Okay, -3 times -19 is 57. Added to 5 is 62. Now, is this in row reduced echelon form? Any rows of zeros should be at the bottom. Well, there aren't any. Okay, so we'll say that's satisfied. The leading entry in every row is a 1. Correct. Okay, for all those leading entries, everything else in that column is zeros. Yep. Okay, the leading ones are staggered from left to right as I read down. Yep. Okay. Now I should actually, this is my end here. This is in row reduced echelon form. So I'm essentially done here. I'm going to replace the labels, so I put in the x and y there. What is the first row saying? 1x plus 0y is 62 or better. X is 62, and the second row, y is -19. We have a solution. Okay? Okay, so that's how we would use Gaussian elimination on that one. Okay, or a way to do it. Okay, let's take another one. 2x minus 5y equals 1. X minus 3y equals 2. Easy. Let's go ahead and write the augmented system. 2, -5, 1. 1, -3, 2. Okay, so we've got that down with all the labels and dashed lines and etc. Okay, so there's our augmented matrix. Okay, now, do you realize what I would like right here is what? I would like a 1, if possible. Now, there's a couple ways you could go to get a 1 right there for that leading entry. You could divide that entire first row by what? 2? And that's probably what a computer would do, because it doesn't care, okay? It doesn't care about saving time or calculations, unless it's programmed to, okay? All right? Your TI would probably just divide that row by 2, okay? It doesn't worry about how much work it is or hate fractions or anything like that. But there's another way of doing it. Do you see I actually have a 1 right down here? Okay? All right. Wouldn't it be easier if I just interchanged these two rows? Then I wouldn't be calculating anything and I wouldn't have any fractions involved. Okay, so I'm just going to interchange the rows. Okay? And if I interchange the rows, I now have 1, -3, 2, 2, -5, 1. I've just in essence interchanged these two equations up here, haven't I? And that's not going to affect the solution in any way. Okay, now I've got what I want where I want it. What don't I like here, young people? I don't like that 2 there. I want that to be a 0. How would I go and use the first row, okay, to change the second row? Okay, I could go -2 times the first row because of the 1 there. -2 times the first row added to the second row replaces the second row. And you can see my notation there. Again, please write that notation when you're working at problems so I see what it is you're doing or attempting to do. Okay, so the first row did not change, so it's still 1, -3, 2. The second row will change. 1 times -2 is -2, added to 2 is 0. -2 times -3 is 6, added to -5 is 1. -2 times 2 is -4, added to 1 is -3. And we've got our second row being now 0, 1, -3. Now, the leading entry in this row is the 1. It's what I want, where I want it. Perfect. Okay, what don't I like about this column now? I need to zero it out, right? I need to zero out that column. How would I do that? Well, right above, I see a -3 there. So I'm thinking about this. If I go 3, so +3 times the second row added to the first row replaces the first row, then we should be in good shape. We should have a 0 sitting right there, and then we'll be done. Okay, so here I just copy down, right? The second row is not itself changing. It's being used to change the first row. So I've got 0, 1, -3. Okay, -2 times the 0 added to the 1 stays 1. Cool, didn't mess that up. Or I'm saying -3 times that added to that is still 1. Okay, -3 times 3 times 1 added to the -3 gives 0. Okay, I'll eventually speak correctly. Okay, 3 times -3 added to 2 is the -7. Are we done? Can you see that this is in row reduced echelon forms? Okay, it's perfect for reading it off. In fact, x is -3 and y is -3. Oh, x is -7, y is -3. Sorry. Looking down here, by the way, we will start doing this. We'll be writing these as matrices also. Okay, not the augmented matrix. Okay, it's just a matrix, an array. Okay, I've got this matrix. It has what? 1 column but 2 rows. It's a 2 by 1, therefore. Okay, the first entry is going to be the x. The second entry is the y. And that's going to be equal to what? -7, 3. These two are conveying exactly the same information. I'll show you why this is sometimes a convenient notation here. Okay? I'll teach you a little bit more about matrices with this as well. Now, I'm doing this out of order from the book, so there's a couple things I'm skipping in here, but I'll throw them in as we go through. Okay? Let's take a look at this one. I got 3x plus 6y is -3. 4x minus y is 5. Okay, write that as its augmented system. 3, 6, -3. 4, -1, 5. Okay, I want a 1 right here. I don't see any. I could add a multiple of this to this and then switch them, but I think I'm just going to divide by 3. So I go 1/3, think of it that way, times the first row replaces the first row. Okay? So then I've got what? 1, 2, -1. Okay, I've got a 1 where I want. Perfect. Okay? I don't like that 4 there. I want to turn it into a 0. So I'm going to go -4 times the first row added to the second row replaces the second row. So I write 1, 2, -1 again. -4 times 1 is 0. -4 times 2 plus -1 is -9. -4 times -1 is 4. Added to 5 is 9. So I've got that. Okay. The leading entry in this second row is not what I want here. I better divide through that entire row by -9. So I go negative 1/9, row 2 replaces row 2. And I've got 1, 2, negative 1, 0, 1, negative 1, looking pretty nice. Okay, so my leading entry in the second row is 1. I do not like that 2 there. I want to turn that into a 0. So I go negative 2 times the second row added to the first row replaces the first row. So I've got 0, 1, negative 1 on the bottom. Okay, I've got 0, 1 because of the zeros here. Okay, in the first column, unchanged. Negative 2 times 1 is negative 2 added to 2 is 0. That's why I did that. Negative 2 times negative 1 is 2. Added to 1 is 1. You can read off the solution here. X equals 1, y equals negative 1. You could write that as a matrix like we did in the previous problem. You know this, x, y equals 1, negative 1. Okay. Forgive me, I'm writing with my mouse here, so it doesn't go so well. Okay, looks a little sloppy. Alrighty, but that's the idea. Okay, it's always a good idea to double check your solution as well, but I assure you these are done correctly here. Okay, let's take a look at this system here. It's just an augmented matrix is really what it is, okay? This is already in row-reduced echelon form. How do you write your solution? I just want to show you here, okay? Is it in row-reduced echelon form? There is a row of zeros this time. It's all the way at the bottom, okay, like it should be. Okay, the leading entry in every row is equal to 1. Okay, good. We've got what? Zeros in the rest of the leading entry rows, right? In the columns, right, of every leading entry. So we got 1, 0, 0, 1, and then we've got zeros above and below. Okay, how many leading entries are there? There's only 2. Okay, these numbers are not leading entries, right? They are not the first numbers you run into in either row reading from left to right. They happen to be what, negative 2 and 3. This does not prevent it from what, being in row-reduced echelon form. Still, the leading entries are staggered as we read down, right, from left to right, okay? So this is it. There's nothing else we can do with it. It's in row-reduced echelon form. How do you actually write the solution here? Let's go ahead and translate for us here what the last row is worthless, right? It's 0 equals 0. But the first row is saying x plus 3z equals 7, okay? The second row is saying y minus 2z equals 5. Do you see how it's easy to solve for x and y in terms of z? Okay, this is what I'm going to do. I'm going to add negative 3z on each side and add 2z on each side in the second one. So we've actually got what? X is 7 minus 3z. Y is equal to 5 plus 2z. Now z is actually going to be z. Okay? In other words, z, we have one free variable here. This actually has infinitely many solutions. Okay? Every time you can choose any z under the sun freely and then generate a corresponding x and y that will give you a solution. Okay? So I'm going to write it in this term in terms of matrices here, and here's where I have to talk about some things from previous sections that I've actually skipped here, but they're really easy here. Okay, well, my solution, some people call a matrix with just a single column or a single row a vector, so I would call this a column vector. Okay, just a single column. Okay, x, y, z, right? So that's my solution vector, is what some people would say. This is actually equal to, see the constants here, 7, 5, 0, okay? 7, 5, 0, plus z times, I'm actually factoring out z from all of these, z times negative 3, 2, 1, okay? Z is free. So you generate a solution for every choice. It's up to you, choice of z, okay? All right. Now to add matrices, it's very easy. They have to have the same dimensions, the same number of rows and columns, and then you just add corresponding entries. Okay? On the other hand, we have something called scalar multiplication. That just means multiplying a matrix by a number. Okay? And that number would be put on the outside like z here. That scalar, or which is a fancy physics term for number, that scalar just multiplies on every single term. Okay? So the z here would multiply on the -3, the 2, and the 1, and we would get -3z, 2z, 1z. Then we added them together, we'd get x equals 7 minus 3z. Okay? We would get these as vectors, but there would only be a single equal sign. Okay? This is what would happen in the end. These would be gone. We'd have a single like that. Okay? Y equals 5 plus 2z. Z is z. Okay? So infinitely many solutions on this one. Okay? Let's look at one more. Okay? I've got 1, 0, 3, 0, 0, 1, -2, 0, 0, 0, 0, 1. All right, now let's look at the last column. This is in row-reduced echelon form here, but let's look at the last column. Or, I'm sorry, the last row. I'm sorry, I messed it up. The last column is just the column of constants. The last row, this would be saying 0x plus 0y plus 0z is equal to what? The constant 1. But you know 0x plus 0y plus 0z is always 0, so this would be saying 0 is equal to 1. That's a contradiction, right? 0 is not equal to 1. What can you say about this system, or the original system that led up to this final augmented matrix, maybe? You could say it's inconsistent. In other words, there actually is no solution to this system. There is no solution, okay? So inconsistent system, that means there's no solution, okay? And inconsistent systems, once you get down to row-reduced echelon forms, you'll always tell they're inconsistent because you'll get a contradiction of this time. 0 equals some non-zero number, okay? All right, let's look at this one. X plus 3y equals 4, 2x plus 6y equals 11. I think you can see that there's actually no solution here. There I wrote the augmented matrix, 1, 3, 4, 2, 6, 11. -2 times the first row added to the second row replaces the second row. And you see here we get a bottom row where we've got 0, 0, 3. Now, if at any point you run into a contradiction, which is always going to be 0 is a non-zero number, then you can just stop and say there's no solution. Okay? All right, so that's an introduction to Gaussian elimination. I hope you understood it. You could feel free, of course, I want you to read the book as well. And I will assign you some problems in this, and you should be okay.